Okay. So we're gonna get kind of a smattering of chemical reactions. We just run the whole gamut, all the way down to equilibrium. And the last part of it is the Le Chatelier's principle. This is an extremely useful principle when you're dealing with equilibrium situations. And then, of course, I need to define what that is. All right. By now, you probably figured that a chemical reaction is any process where beginning substances are changed into ending substances. They have to be, the identity of the substance has to change in order to be a chemical reaction. And we divide them into these various types just to try to make sense of the world. And there is overlap, and some reactions can be one of each, or sometimes there three of them can be applied to a chemical reaction. A combination or a synthesis reaction is when you have two simple reactants and they become some more complex. You just put things together. And if you turn around and take that and break it apart, that's called a decomposition. We'll do some examples too. Displacement. Another name for that is single replacement. I like single replacement better. It's more descriptive. If you have an element here and a compound here, then you just swap one of them out. So let's say this is a metal. So there's your metal. We'll have A, C plus B. That's a single replacement. Let's see, I think one that you guys did in lab was zinc metal and hydrochloric acid, and the zinc replaced hydrogen, like that. And you had bubbles. The hydrogen gas was the bubbles. That's a single replacement. Double replacement or an exchange reaction is just the next step above this one, where you actually have two compounds, and then say these two swap places. So now you have an AD and a CB, because we always write the metal first. Let's see, what's an example? How about silver nitrate and sodium chloride. And these are in solution. So silver replaces sodium, and you get silver chloride plus sodium nitrate. I have to run off the edge of the board there. That's a double replacement. Very often these double replacements, while this may be in solution, these both are in solution. This one's still in solution. This one makes a solid. That happens a lot when you have double replacement. In fact, I think for a double replacement to work, one of the phases on the product side has to be different than this side. So you've got to make a solid, you've got to make a gas, something different in order for the reaction to drive. If everything's aqueous front and back, there's really no reaction. So we make a precipitate here. That's what the solid is called. Y'all did one of those, didn't you? I think. And it turned kind of cloudy.
I'm sure.
Yeah. Oxidation reduction reactions. These are reactions where electrons transfer. Now the reaction, when you write the reaction out, it may not show the electrons being transferred. In other words, the electrons, when they transfer, are kind of going in the background. So you need a way to determine whether an oxidation reduction has taken place. And oxidation reduction reactions can also, well, if you have a combustion, and combustion always involves oxygen, something plus oxygen yields something else. The combustion reactions are always oxidation reduction. A galvanic cell is like a battery, right? So you know electrons are being transferred there. Any of these dry cell batteries in this thing, electrons have to be transferred, or otherwise this thing won't work. Electrolytic cell is the other direction. A battery discharges to give you electrical power. An electrolytic cell is the opposite direction. You drive the reaction in reverse by putting electrons in. So that's what happens to the battery under the hood of your car. When you start it up and the alternator starts sending power through the electrical system, goes into the battery and recharges it. So these are reverse of one another. Okay. All right, so the synthesis reaction is like this. Here's an example. Calcium and sulfur, right? That's a metal. That's a solid. It's a non-metal, but it's a solid. And this is a solid also. But you just combine these two elements and you get a compound. That's a synthesis. A decomposition where we have copper 2 oxide. And usually, I think what you have to do is heat it. Just heat it up, and it'll decompose into copper and oxygen. Here's a single replacement, an example of a single replacement, where iron replaces copper in this compound. By the way, this is also an oxidation reduction reaction. So how do we know? Well, we have a method called oxidation states. It's sort of like charges on ions, but not really. It's more like a bookkeeping scheme. I think we're going to do some of that, aren't we? We better. Yeah, we are going to do that. Okay, so I'm not going to hammer that one right now. It's just to make note of the fact that sometimes you can use simple rules of thumb. If all you have to do is identify it as an oxidation reduction reaction, if this is elemental on that side and it's a compound over here, that's an oxidation reduction every time. Or if it's an element over here and it came from a compound, that's an oxidation reduction reaction. Electrons have to be transferred for that to happen. Okay, double replacement. Oh, they use my example. Okay. And that's true. It's often accompanied by precipitation. But it could work if a gas is produced. Combustion reaction. Here we go. This is propane. Right, so everybody's barbecued with propane or heat your house with propane. That's what happens when you combine it with oxygen. You get carbon dioxide and water. And this is an oxidation reduction reaction also. Okay, so what kind of reaction is this? We got a compound over here, and we've got more simpler versions over here. This should be considered a decomposition. There's no replacement taking place because there's only one compound over here. And we just heated it up and you get nitrogen dioxide, water, and oxygen gas. So that's a decomposition. Sometimes decompositions are mistakenly identified as a compound becomes elements and a synthesis elements become compounds. But it doesn't have to be that way. All you need is for complex to become simple, or the other direction, simple to become complex. Let's see, how about these? What are our choices? Combination, decomposition, displacement, single replacement, exchange or double replacement, and combustion. Now, there could be several answers for these. Okay, this is going to be a single replacement, right? Magnesium. So this one will be displacement, they call it. But you've also got an element here and a compound over there, so this is redox. And that's our short version for oxidation reduction. We call it redox. Let's see, combination, exchange, displacement. I think that's it for this one. Displacement. Okay. Oh, that wasn't one of our choices, was it? Okay. It is a redox, though. It's also a displacement, single replacement. This one's a combination. Complex becomes simple, becomes complex. And this one should be a combustion. That's a bad color choice. I wonder if that's even going to show up on the video. Difficult. Okay. So I mentioned before, oxidation reduction reactions are those in which electrons have been transferred. And a lot of reactions, electrons are not transferred. But in the cases where you do have transfer of electrons, it sets you up for a useful reaction for extracting energy from the reaction. If the reaction is exothermic, then okay, you might be able to get energy out of it. But if you can transfer electrons, then there are much more efficient ways to get energy out of that reaction. Simply by taking part of the reaction and putting it over here, the other part of the reaction and putting it over here, and then send the electrons through an external circuit. Right? Instead of going straight from one reaction to the other, you send it through an external circuit. Now you can grab those electrons as they're moving and make them do work for you. That's what batteries do. Right, I mentioned this one also, this rule of thumb. Element becomes a compound or is part of a compound, you definitely have a redox reaction. Okay, oxidation states. This is a bookkeeping method. And it's kind of like determining what's the charge on your ions. But you can use the method for covalently bound compounds. They don't have to be ions. So that's why I call it a bookkeeping method. It's just to keep track of the electrons, where they're most likely to be, and then you can watch them move during a reaction. So how do we do it? Well, rule number one is if you have an element, its oxidation state is 0, like sodium metal. Its oxidation state is 0. And we usually put that value, oxidation number, up here where we would normally put a charge in that position. Remember, 1, 2, 3, 4 places here. And for sometimes it does equal a charge, but not always. So elements are always 0. Even if you have, say, a diatomic element like hydrogen, each atom is 0 oxidation state. Okay, the oxidation number of any ion is the charge. So if this sodium becomes an ion, right, say in aqueous solution, then that +1 is its oxidation state. These are the easy ones. For the alkaline metals, the group 1A, those are always +1. So if they're in a compound, like this one, that's always +1 oxidation state. Or lithium, potassium, sodium, rubidium, cesium, they're all +1s. The reason we have to make these rules is because some of the elements can have multiple oxidation states. If you look at, let's see, there's a copy of the exam. But one of the last pages on the exam has a periodic table on it. If you look in the corner, upper right-hand corner of each of the little boxes, some of them have multiple, what look like charges. In fact, they're on this one too. Like there's chlorine, you can see, like it has 6 of them up here. Those are not charges. Those are oxidation states because they're valid for these elements when they're in covalent compounds. And in covalent compounds, you don't have charges. So these numbers represent oxidation states. And since these are variable, then we need to fix a few of them. So if they're in combination with some of these elements, like, let's see, what's an example? How about phosphorus trifluoride? Right? What's the oxidation state on phosphorus? We don't know. It could be multiple charges or multiple oxidation states. So we fix fluorine at -1. That's one of the rules. It's probably on the next slide. Fluorine is always -1. The ions are always the alkaline metals are always +1. Alkaline earths are always +2. The oxidation number on hydrogen is +1. Unless it's in certain types of compounds, like if it's combined with a metal, like, let's see, it's a good example. How about that one? Aluminum trihydride. Now, aluminum is the one that's the positive, because it's the metal, and hydrogen has to be -1. Okay, those are exceptions. But when hydrogen comes first, like in an acid, it's always +1. Okay. Let's see. Oxygen is taken as -2. And remember, in the beginning, when we were learning to name compounds, we said these are +1, +2, +3, -1, -2, -3. Those rules. We're sort of morphing them into another use now. Oxygen and all the chalcogens generally are -2, except that we fix oxygen at -2 because it's part of a lot of different compounds. So if we fix it at -2, then it makes, we're able to calculate the oxidation state for the other elements. There's only one exception. When oxygen is bound to another oxygen, that's a peroxide. And you have something else here. Could be anything. If you go to your medicine cabinet, pull out that brown bottle. That's hydrogen peroxide. Okay, both of those R's are H's. But peroxides come in all kinds of shapes and sizes. And in this case, each oxygen is -1. So the total for this one is -2. Okay. That's the only exception for oxygen. Yeah. Brought my own. Okay. Oxygen. Let's see. Binary compounds. The more electronegative element is assigned the negative oxidation number equal to its charge in the binary compound. So what we're talking about here is two nonmetals that are bound to each other. For instance, nitrogen and oxygen. Okay. In this case, oxygen is more electronegative, and we're going to fix it. That's a bad example because oxygen is always -2 anyway. So that means nitrogen would have to be +2 to balance it. Let's see if I can figure a better example. How about carbon and sulfur? Like that one, carbon disulfide. The more electronegative, well, that's not a bad example, good example either, because they're almost equal. But in this case, the second one is normally considered the negative. The way we write compounds, carbon with positive. You have to actually assign -2 to sulfur because it's in the oxygen's group. And that means this one is +4. I'm not coming up with good examples right now. Maybe we just better move along with the rules and work some samples. When you add up the numbers, the oxidation numbers for your compounds, the neutral compound, the oxidation numbers have to equal 0, just like charges would have to. So if we had, okay, here's an easy one. Water. Right? Hydrogen's +1, water's -2. So 2 times +1 is +2, and 1 times -2 is -2. So 0. We can extend that rule to polyatomic ions. Polyatomic ion, isn't it? Oh, there it is. Polyatomic ions would be equal to the charge. So NO3 minus oxygen's -2, right? So -2 times 3 is -6. Total for oxygen. But we need to keep a negative out for the charge on the ion. Right? So we really only have to balance 5 of them. That means nitrogen is +5. And if you add this one together with that one, you should get that one. So polyatomics always have to add up to the charge on the ion. Okay, so let's do some examples. Oh, here's a big one. Potassium Dichromate. This is a neutral compound. Potassium is an alkaline metal, so it's +1. Oxygen is taken as -2. Okay. So now we can calculate what chromium is because we've fixed these values for those two. So this one contributes +2, since there are 2 of them. This one contributes -14. 7 times -2. So together, these two are -12. That means chromium has to balance that -12 with a +12. So if a +12 for both of them, each one has to be a +6, because there are 2 of them. So now we know the oxidation state for chromium. Let's see. Oops, skip ahead. Okay. The carbonate polyatomic ion. So we have -2 for oxygen, -6, but we need to make sure that we have -2s, 2 minuses that are left over, that are not neutralized. So we really only have to balance a -4 from these oxygens. So that means this one carbon has to be +4. Right? +4 and -6 is -2. Okay, we can do that for each one. We can probably do this one in our heads. Oxygen's -2, so that's -4 total. So manganese has to be a +4. Okay. PCl5, that one is a little more problematic because we didn't establish what chlorine should be. But since chlorine is more electronegative than phosphorus, we're going to fix chlorine at the charge that we would normally find for a halogen, -1. Same as fluorine. That's the only way we can solve the problem. Otherwise, we're stuck. So, and since this is a bookkeeping scheme, this generally works. So we have -5 total for chlorine. That means this one phosphorus has to be +5. Okay. The next one is simple because we know fluorine is -1. It's always -1. So 4 minuses are balanced by +4 for sulfur. Okay. Now, don't lose sight of the fact that we're not learning how to do this just to aggravate a student on a test. We're learning how to do this so that we can track electrons in reactions. Okay, so if we're trying to determine if a reaction is redox, we do the oxidation states for both the reactants and the products, all their elements, and then we look at any changes that take place during the reaction. If there's no changes, then it's not a redox reaction. Okay, here's a pretty good one. Calcium metal and chlorine gas. Set those off and you're going to get a violent exothermic reaction. Okay, oxidation number for sulfur in sulfuric acid. Okay, this is +1. Oxygen's -2. So we have a +2 for the hydrogens. We have a -8 for the oxygens. These taken together are -6. So that sulfur has to be a +6 to balance. Okay, during a chemical reaction, if the reaction is redox, the transfer of electrons always occur from one place to the other. So we identify oxidation as a loss of electrons. Okay. Oxidation is loss of electrons. So that means if one atom is losing electrons, some other atom has to gain electrons. In a chemical reaction, we don't have static charges. It's always neutral. So the electrons, they can move, but they can't, the balance has to be maintained. So if electron leaves one place, it's got to go someplace else. And that's called reduction. When the electrons are received by something else, that's called reduction. Is gain. So that's why the acronym oil rig is useful. Oxidation is loss, reduction is gain. Now, the object that is oxidized is causing the reduction of something else. So that's why we call it the reducing agent. So whatever is supplying electrons, giving them up, is the reducing agent. And whatever is receiving the electrons is the oxidizing agent for that other species that's being oxidized. So that's the terminology. Okay. We're just beating a dead horse over here. Just never lose sight of the fact that when you have one, you always have the other. They always occur in pairs. Okay, when we look at the numbers, we've got these oxidation states. When something is oxidized, the oxidation number increases. Even if it's negative, it will become less negative. So oxidation means an increase in oxidation state, whereas reduction is a decrease in oxidation state. It either becomes from a positive number to a smaller positive number, or it may even go all the way into the negatives. For instance, this one has an oxidation state for carbon of -4. If we burn it, like a combustion reaction, it'll produce carbon dioxide and water. Let's see. I want to balance this one. That's balanced, okay. So over here, this is -2, -4, so this is +4. So in this reaction, carbon has gone all the way from -4 to +4. So it's increasing its oxidation state in this reaction. So how many electrons were transferred in the process? How many did carbon lose, right? It has to lose electrons to go more positive. So I think of it this way. How many does it have to go to get to 0? Right? To 0, that's 4 electrons, right? Then it goes to +4, that's 4 more electrons. So it's 8 electrons had to be transferred from carbon to something else. Well, the hydrogen didn't change. It's +1 here and it's +1 there. So it must be the oxygen. Oxygen 0 there, and here it's -2. And here it's also -2. So they actually went 2 places. This oxygen changed from -2 to make that compound, and -2 also to make that compound. So it didn't just go one place, it went 2 places. But it ended up at the same oxidation state. Okay. All right. So let's see. What is oxidized and what acts as the reducing agent? Well, if it's oxidized, whatever is oxidized acts as the reducing agent. So what do we have here? Copper, 0 oxidation state. Silver nitrate. Okay, yields silver plus copper nitrate, and then some sprawling off the board. Let me scoot it just a little bit. I think I can get away with that. There we go. Okay, we'll do the easy ones first. That one's 0. This one's 0 because they're elemental. For this one, we know nitrate is a -1 charge for that whole group. And over here, it didn't change at all. It's the same on both sides, right? So nitrate's not involved at all in the oxidation reduction. It's an exchange between copper and silver. On this one, since that one's -1, this one has to be +1. Right? And this one is 0, and this one has to be, let's say, 2 minuses. This has to be +2. Okay? So, what's oxidized? Which one loses electrons? Oxidation is loss. Well, which one went positive? Copper went from 0 to 2+, so it lost electrons. And it's also the reducing agent. It transferred electrons to silver and caused it to be reduced. So when I want to keep track of electrons in this scenario, I do it like this. Over here. That. This was a loss of 2 electrons per copper atom. Then while we're at it, since we're going from silver here to silver there, this was a gain of 1 electron per silver. Now, what's wrong with that picture? The number of electrons so far, the number of electrons lost is not equal to the number of electrons gained. You've got to balance it. Well, fortunately, this equation is already balanced. So we can see that if it's 1 electron per silver, there are 2 silvers. Now everything's kosher. 2 electrons from here went over there. 2 electrons went from here over there. The electrons always have to balance. Okay, so copper is oxidized and it is the reducing agent. All righty. Let's see. Which of the following are oxidation reduction reactions, and identify the oxidizing agent and the reducing agent? Okay, so the first one, we can use that clue. Right? We've got an element here, and it's ending up in a compound over here, so we know this one's redox. That's definitely redox. But it also wants to know which one's the oxidizing agent, which one was reduced, which one gained electrons. Well, I think the hydrogen went from +1 to 0, so it had to gain electrons. It is the oxidizing agent. Okay. That means zinc is the reducing agent. That doesn't mean rheumatoid arthritis. It's reducing agent. So zinc went from 0 to +2. So it had to lose electrons. It is the reducing agent. It supplied electrons to to this one, which was being reduced. Okay, so we got that one identified. How about this one? We do oxidation states. Well, let's see. Hydrogen's +1, oxygen's -2 here. Right? That means that we have -1 charge, which is kosher. Over here, -2 for oxygen, +1 for hydrogen, that's balanced. So nothing happened to oxygen and hydrogen. Over here, it's -2 for oxygen. Over here, it's -2 for oxygen. So what's going on? Chromium could change, possibly. Let's see, what is this one? -2 and 7 is -14. And then we need to hold 2 of them out. So -12 is balancing for +12 chromium. That means chromium is +6. How about over here? 4 and -2 is -8. We got to hold 2 out for the charge. So -6, chromium +6. That's not a redox reaction. I would also add that this is an incomplete reaction if it were redox, right? Because even if chromium were reduced or oxidized, where are the electrons going? Right? They can't go here, they can't go there because nothing changed. Right? So this is not a redox. Okay, how about, let's get this out of the way. How about this one? Well, we've got one compound here. Oops. We got one compound here that's becoming a compound and an element. So chlorine, we have to take as -1. And over here, chlorine is -1. So 2 minuses means this one has to be a +2. And this one's a 0. What's copper over here? Well, 1 copper and 1 chlorine, that means this is +1. So what we've got is the copper is going 2 different directions at once. It's going to a +2 here, which means it's oxidized. It's the reducing agent. And here it's going from +1 to 0. It's being reduced. It's the oxidizing agent. But notice also you've got 2 here. So it doesn't happen to the same copper. It's like writing it this way. Like that. Now one of these goes over here and the other one goes over there. Okay? That is an oxidation reduction reaction. It's got a special name, actually. It's called a disproportionation reaction. See, there should be a box come up with this one, too. Here we go. So in this case, copper chloride is reducing and oxidizing agent. And that's, let's see. There we go. Copper smelters will use this reaction when they mine the ore. All you have to do is heat it up, get it really hot. Oh, now this is an aqueous solution. Okay, so some other reactions going on. You could powder it and heat it up real hot, and you could get this reaction, but this one's occurring in aqueous solution, so that doesn't work. Anyway. So, rather than try to invoke this law or that law as to which one works, we're going to look at these reactions in terms of theories. And the best one that works is the collision theory of reactions. And it's really simple, actually. Think of it this way. If you've got an atom or a molecule, and it's supposed to react with some other atom or molecule, right? They're not going to react unless they come together. So they've got to collide in order for the reaction to occur. So you have to have a collision, and you have to collide with enough energy to start the reaction. That's called the activation energy. You got to put in enough energy to get it to a certain point, called the transition state. And if you do, then it potentially could go just a little bit more than the maximum that's needed, or the minimum that's needed, a little bit more, then you can go down and make products. But what else is involved is not just the collision and how much energy in the collision, but are they oriented properly? Because some molecules, well, most reactions actually, if they collide this way, but the reaction site's over here, nothing's going to happen. So that's it. They just bounce off and nothing happens, no matter how much energy they have. They have to arrive at just the right geometry in order for the reaction to occur. So these three conditions are required for a reaction to occur. Now, an exception, I can think of one exception to that, is if the reaction only involves one molecule, right? But the decomposition reaction. There, all you need is enough energy to break some bonds, splits apart. So that the collision isn't required. But you do have to have enough activation energy, and the orientation is irrelevant too for a decomposition. But in general, if you have two or more molecules or atoms involved in a reaction, they have to collide. And in fact, the more of them you have, the lower probability of the reaction occurring, right? Think about it. If you just have two molecules coming together, all right, there's some chance that'll occur. There's some chance that it won't occur. But if you have to get three of them together with just the right energy and just the right orientation for the reaction to occur, then the probability of that happening is infinitely less likely than if you have just two that need to come together. And the more are required to come together, the harder it is to do, statistically speaking. Okay, I mentioned that already. I mentioned that one already. I mentioned that one already. And this is your author's idea of visual explanation. Orientation and energy are correct here. So notice that this carbon monoxide is going to pick up an oxygen off of that nitrogen dioxide and leave you with nitrogen monoxide and carbon dioxide. Okay. So they have to be oriented so that we can form a bond between these two and break that bond. If they come together like this, nothing happens. Like that, nothing happens. Like that, nothing happens. Or rather than saying nothing happens, the reaction that you expect won't happen. You could get a different reaction.
So your next time I'm here will be darker.
I can hardly wait. I'm happy to just have hair. Okay, so these three factors are necessary for a reaction. The lower the activation energy, the more likely the reaction will occur. The more collisions there are, the more likely. And the more likely you are to have orientation, the more likely to react. Okay. So I've used these terms before, and I'm not sure if I've defined them. The difference between an exothermic and an endothermic reaction. It's instructive and useful, I think, to think of reactions in terms of whether they're part of a system. So the reaction occurs inside this system. So you have your reactants in here. And when the reaction occurs, there are three possibilities for energy transfer. This is the surroundings. Now we're talking about thermochemistry, chemistry involving energy transfers. So if the reaction occurs and energy leaves the system, right, and we give that a little symbol Q. That's heat. If that leaves the system, then we've got an exothermic reaction. But if during the reaction it absorbs heat from its surroundings, we have an endothermic reaction. And this is derived from the prefixes, exo meaning out of and endo meaning into. Okay. And thermic, of course, is heat. So we usually associate exothermic reactions with combustion reactions. And that's accurate. Combustion reactions are always exothermic. But there are some reactions that absorb energy. This may not be the best example, but it illustrates absorbing energy from the surroundings, as if you're in a hospital setting. I think they still do this. You know, if your patient needs a cold pack of some kind, then you just throw some ice in a bag and put some water on it, zip it up, give it to them. But you also have available to you many times a cold pack with it's sealed and it's got water in it, and it's also got a little capsule in there of chemical. And if you break that chemical and mix the water with it, then it'll either get cold or hot, depending on what the chemical is. So cold packs and hot packs are made that way. And the reaction that's taking place, the dissolution reaction, actually, will either give up energy or absorb energy in the process. Now, when we're talking about an actual chemical reaction, it's useful to think of them as what's happening to the bonds in the reaction. We're breaking bonds and forming bonds. If you have, for example, if you have A with B and C with D, and then they swap places, so we have C with B, have a bond there, and A with D. Okay, how much energy does it take to break these bonds? You got to put energy into it. So that part is endothermic. So you put energy in to break the bonds. It could be Q, it could be any kind of energy. So we're energy going in. And then when the bonds reform, that produces individual A's and B's and C's and D's. Then when the bonds reform between C and B and A and D, the bonds reform, you get energy back. Because this is a more stable situation. It's a lower energy state. When you have individual atoms coming together to form a bond, they do that because it's more stable. So you get energy back in this process. Well, let's see. There's 1, 2, 3, and 4. Okay. The process is exothermic. If you get more energy back than you put in. If you put some energy in, but when the bonds reform, it gives up more energy. That's exothermic. Okay, that's what happens in a combustion. If, on the other hand, you have to put a lot of energy in to break the bonds, but you only get a little bit back, that's endothermic. Okay. I like to think of that in terms of how you make nitroglycerin. Right? You put some energy in with glycerol and nitric acid, a little sulfuric acid to facilitate, but basically it's the nitrate part of the nitric acid combines with the glycerol, makes those bonds, right? But you have to break bonds, you have to separate. The glycerol, you have hydrogens bonded to oxygen, you take them off. So you're putting energy in. And it takes a lot of energy to do that. And then when the bond reforms, where the nitrate forms where the hydrogen was, we only get a little bit of energy back. So that's endothermic, and that energy now is stored in the bonds. Right? They're locally stable, but if you disturb it, then you get a lot of that energy back that you put in. So that's how we make explosives. We put a lot of energy in that stays in the molecule until we need it. But it's a balance. It's a balance between energy required to break bonds and energy you get back by forming new bonds. This is another way to look at it. Here we have, this is just, the reaction is progressing. Right? Over time, it moves from reactants to products. This is the amount of energy in the system, the whole system. So in this case, we're starting up here with an energy level for our reactants at this place, and we have to put some energy into it. This is called the activation energy, to go from here to here. If we can get enough energy into it, and of course, orientation is, geometry is correct, then just a little bit more of that energy, and now it rides down the other side. And this is the amount of energy that it gives up in the process. From here to here is the total energy given up when bonds form. And over here is the amount of energy put in. So the difference between the two is this amount. So the difference between the energy of your reactants and the energy of your products is the energy of the reaction. In this case, we have less energy in the products than in the reactants. So that is exothermic. Yeah, exothermic. We gave up energy in the process. I think the next slide is probably the other way around. I'll come back to that one in a second. So in this one, we start out low energy in reactants, in the high energy for the products. You put in a lot of energy and you only get a little bit back. So that's an endothermic process. And the example they use is photosynthesis. Right? The plants are storing energy. In an endothermic process, they're storing energy in Well, in the simplest terms, they're taking carbon dioxide and water and making simple sugars and carbohydrates of some kind. They're making starches, or trees will make cellulose, or they'll make anything else they need for the cells to work, like proteins, nucleic acids, fats, whatever the case may be. They make more complex molecules and they store energy that they have extracted from sunlight. Okay. Now that's most plants. There's some microorganisms that will extract energy from chemical reactions. They call them chemotrophs, which is a fancy word for chemical eaters. So this is an endothermic process. Farmers depend upon it to make a stored energy product that they can sell on the market. I was listening this morning on the radio. They were giving a soybean report. And this year, the USDA is estimating less soybean production from all the farmers across the US. But that's counterbalanced by the fact that we're not exporting as much. Okay. Which of the following statements is correct? During an exothermic reaction, the average energy of the products is higher than the average energy of the reactants. No, it's an endothermic process. Endothermic reaction, the average energy of the products is lower than, now it's an exothermic. So this word ought to be down here and this one ought to be up here. During an exothermic reaction, the average energy of the products is lower than the reactants. That is true, exothermic. Okay, we can also study how fast a reaction is occurring. Some reactions are what we would consider spontaneous. They will occur, just put the reactants together and eventually they'll make products. But that doesn't tell you how fast it occurs. Sometimes it's useful to know just how long it takes for a reaction to occur. Diamond, for instance, is unstable in oxidizing atmosphere where there's oxygen. And it will spontaneously decompose, exposed to oxygen. Only it'll take it probably 100 or 200 million years to happen. It just doesn't occur very fast. But some reactions, when you put them together, they will go like that. They use that in spacecraft. When you don't want a complicated system in your rockets for maneuvering purposes, where you have to have an ignition source and safety measures, then you design your reaction mixtures so that you have one chemical here and one chemical here, and you know when you put them together, they're going to react immediately. Those are called hypergolic propellants. And those are used usually in reaction jets on spacecraft. So all they have to do is mix them and they get that push instantly. Unlike the main rocket engines, where they usually have kerosene and oxygen, or methane and oxygen, or some hydrogen and oxygen, they have to have an ignition source to get them started. So studying the rate of reaction is important. How fast are reactants consumed to produce your products over a given period of time? So what affects the reaction rate? Well, first and foremost is, what are the reactants? And what physical condition are they in? In other words, you can't get them to collide if they're big chunks of solid and you just put them together like that. The only interaction you're going to get is at the surface where they touch. So if they're powdered or liquid or in solution where they can be intimately mixed, then you have the opportunity for those collisions to occur. That's one of the reasons that coal mines are so dangerous, because in the process of mining, you produce that dust, very, very fine coal particles, which are flammable in an oxygen atmosphere. And you have to have oxygen down there for the miners. They can't all run around all day with breathers on. So you have to keep the dust level down. And that's one of the safety measures that inspectors check for. They have a special device with a filter in it, and they take a sample. It sucks air through and through the filter, and then they take that filter to a lab and analyze it to see how many particles per cubic meter or cubic foot or whatever the unit they use. And they know that above a certain level, you're unsafe. So, and that's because that with a small particle size, you get much more contact with the fuel and the oxidizer. So the physical nature, how finely divided are they, or what phase are they in, will determine the speed of the reaction. How concentrated are they? Right? The more concentrated, the higher the rate. Most reactions get faster when you increase the temperature. Are there any catalysts? We know what a catalyst is. A catalyst is anything that speeds up a reaction. It doesn't become part of the products. It participates in the reaction, but it goes in one end and it comes out the other, seemingly unchanged. But it speeds up the reaction. Think about catalytic converters in your car. They put them in line with your exhaust system. Internal combustion engines are not as bad as they used to be, but they still produce incomplete combustion, products that are not desirable for the environment. So the government has said, all right, you got to put these devices, but before you send the exhaust out in the atmosphere, you got to put this device in there that will finish the reaction. That's the catalytic converter. And it takes various products like oxides of nitrogen, or incomplete carbon compounds like carbon monoxide, and finishes converting them and to produce carbon dioxide, nitrogen gas, and water. That's what you want coming out of your tailpipe. And they use catalysts to do that. Okay, those will alter the speed of a reaction. So what's the physical nature of the reactant? I mentioned that earlier. It's either a solid, liquid, or a gas, or in solution. Particle size has a bearing. I mentioned coal dust. When the reactants are in the same physical state, usually the reaction occurs faster. So if they're liquid-liquid, they mix together, or if they're both a solid state, but they have to be very finely divided in order for that to work. But the fastest rates occur between gases, because gases always form perfect solutions. The mixture is perfect. It's homogeneous, and they're intimately connected. So you can get a faster rate out of a gaseous reaction. That's why the worst explosions in history involve gases. Yeah, I mentioned this one already. Coal dust explosions. They're not too common anymore, but when they occur, they can be devastating. Concentrations, right? How do we measure concentrations? Well, it could be percent by mass. It could be mass per unit volume. It It could be molarity. Any units will do. As long as you increase those values, then you can increase the speed of the reaction. Increase the temperature. When you increase the temperature, you generally put enough energy in there to overcome the activation energy. Right? So when you got that hump here, and you're trying to make that difference right there. Activation energy, when you increase the temperature, you're adding more energy. So you're helping it get to that peak so you can make products. And the catalyst simply provides the reactants an alternate pathway to their products. It doesn't change the products that are made. It only changes the speed with which they act. Sometimes you can think of catalysts as getting involved in that collision theory, the collision model, where it allows the reactants to be properly oriented when they collide. Or it could reduce the activation energy, which often happens when a catalyst is involved. It decreases the activation energy, which means at that same temperature, the reaction is going to go faster because it doesn't have to meet that higher hill. The hill comes down slower. Like, do like this. With a catalyst, it might do like this. Lower activation energy. So without catalysts, living systems would not exist. We have a special name for those catalysts. It's called enzymes. Enzymes promote reactions at higher rates. But actually, enzymes go one step beyond catalysts. Inorganic catalysts like platinum in your catalytic converter, or let's see, did I show you guys the reaction where hydrogen peroxide was catalyzed with iodide? I didn't show you that one. Usually put a colorant in there, like food coloring, in the bottle with your hydrogen peroxide, and then a little soap to make it foamy. And then you dump your potassium iodide in there and it goes just it decomposes rapidly, produces oxygen. Those are chemical catalysts. Enzymes are biological catalysts, and they do speed up the reaction, but they also control the reaction. Which direction is it going? Not just how fast is it going. And with enzymes, with catalysts, they catalyze the reaction in both directions. Okay? But with enzymes, they generally only go one direction. So if you want the reaction to go reverse, you need another enzyme that's designed to go the other direction. So that way they control the reaction. All right, so I mentioned that one just a minute ago. We decrease the activation energy with a catalyst. Okay, what's the function of a catalyst in a chemical reaction? Increasing the rate by decreasing the activation energy. That's a pretty good summation of what catalysts do. Okay, now that we know that reactions can occur at different rates, let's look at what does that rate have to do with the balance of a reaction. We've been writing reactions up to now with a single arrow between reactants and products. But the fact of the matter is, reactions go both directions. You can make reactants out of products, products out of reactants. Now, depending on the reaction, it may prefer to make mostly products. You know, like a big arrow this way and a tiny arrow that way. Or it could go the other direction. we need a way to express that difference. Okay, so when this is happening, you will have a certain amount of reactants over here, certain amount of products. At some point, they seem to appear as if they're standing still. The concentration of reactants on this side and the concentration of products on that side are the same, right? They reach a point in their reaction where they're not changing. That's what we think. At the microscopic level, the forward and the reverse reactions are occurring at furious rates. The reason we don't see a difference is because those rates are balanced. So the rate of the forward reaction equals the rate of the reverse reaction. When that happens, we call that equilibrium. This is another way to look at it. If we're reacting hydrogen gas and iodine, which is a solid, to produce hydrogen iodide, then the reaction rate in the beginning, the forward reaction is all there is, right? There's no reaction going in reverse. This is the reverse reaction. This is the forward reaction. In the beginning, you only have a forward reaction. But as you produce more products, you start to get the reverse reaction kicking in. And at some point, both reaction rates balance, they're equal. And now we have a certain amount of product and a certain amount of reactant still there, and they're going backwards and forwards at the same rate. If we look at it in terms of concentration, you'll see the concentration of hydrogen and iodine decrease and then become constant. And you'll see a production of hydrogen iodide increase until it becomes constant. This is what we see in the macroscopic world, right there, those concentrations. And this is at equilibrium. We think of chemical reactions as reversible, and they are in general, where you have products that can become reactants, and reactants can become products. With that frame of mind, all reactions are reversible, but some of them are more reversible than others. In other words, some of them tend to form roughly equal amounts of reactants and products, but others might form almost completely products. Some of them might prefer to stay reactants and not go to products. So it runs the full gamut. Okay. This is known as chemical equilibrium, and it involves reversible reactions. Okay. Now we're going to, am I out of time yet? I'm not out of time yet. 11:30. Oh, okay. We're still good. So for this reaction, if we write it like that, that kind of obscures the concept that we've been working on. Water and carbon monoxide, that's better. The double barbed arrow is accurate. Okay, the reaction can go both directions. At some point, say we've reached equilibrium. So for this combination of reactants producing those products, now the rate, the forward rate that, let's see, rate to the -1 going backwards, those rates are equal. So now we've established a certain concentration here, 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 and here. Now, what happens once we've reached equilibrium? What happens if we add more water to the flask? So we're going to add more of this one. What is the reaction going to do in response? Does it just sit there? We increase the concentration of water, then nothing happens to the rest of it. No, that doesn't happen. When you add this reactant, some of it is consumed. If there's any carbon monoxide left, it will react with that and produce these until the balance is reestablished. Because the reaction rate is dependent upon concentration. If you increase the concentration here, you get more forward rate until you build up some of this and the reverse rate balances again. This is the basic idea for Le Chatelier's principle. And that's coming up. But stream of consciousness, anytime you have an equilibrium situation in a reaction and you do anything to disturb it, the reaction, almost as if it has a personality, will respond in such a way as to reduce the influence of that disturbance. It will, the fancy term is mitigate. So if you add this one, some of it will be consumed until you reach a balance again. So what about the concentration of water? If we add more water, does the concentration of water go up? Well, yeah. In the beginning, a lot, and then it uses some of it, but it didn't use all of it. It only used enough to reestablish the balance. So the concentration of water did increase, but also you used up some of this and you produced more of that and that until you get that balance again. If we add more hydrogen, it goes the other direction until equilibrium is reestablished. The same thing can happen if you remove either one of the reactants or one of the products. Say we remove some of this. Now the reaction is going to shift this way because we've taken away some of the reactant. The reaction is going to reestablish equilibrium by producing some of this until the balance is reestablished. Now, there's a way quantitatively to express this equilibrium. And it's called the equilibrium constant. We give it a big K. And the K is constant if the temperature does not change. If the temperature changes, you get a different constant. But at a fixed temperature, all you need to know is the concentration at equilibrium of the products and the reactants. And then you write them in these terms. So for this reaction, let's see, is that balanced? H2, 2 O's. Yeah, that's balanced. You would write them like this. Products. And I use square brackets for equilibrium concentration, like molarity. Or since these are all gases, we could use partial pressures. And then CO2 here, divided by the reactants. Water and carbon monoxide. Right? If we had any coefficients in here, like a 1, like a 2, 3, or 4, whatever, they would become powers for each one. Like if there was a 2 here, it'd be squared. Okay, so that's the equilibrium constant for this reaction. And once we know these concentrations, that's exactly what I called it. It is constant. So if we change any of these, then the others have to change in order to maintain that constant. This is the mathematical reasoning behind Le Chatelier's principle. Here's an example. It's called the law of mass action, which means that, actually, I don't know what it means. This one ought to be a small y here. Actually, I like to write it this way. I use a little a here, a little b here, a little c here, and a little d here. That way you can tell which one belongs to which. So this one would be a little c, this would be a little b, this would be a little a, this would be a little b. Those are the coefficients of the reaction, and they're used as powers of the concentrations at equilibrium. So with that information, if we know the equilibrium constant and we have a balanced equation, then if we know three of these, we can find the fourth one. So we can calculate the equilibrium concentration based upon this equation of any of the factors. Or if we know all the factors, all the concentrations here in a balanced equation, we can calculate the equilibrium constant. All right. Right, I mentioned square brackets. We always use square brackets for equilibrium concentrations. And to keep it simple, we'll fix our gaze on molar concentrations, like moles per liter. And you can do that for gases. So many moles per liter of the container. And by placing the product in the numerator and the reactant in the denominator, we can get an idea from the constant which way the reaction tends to go to reach equilibrium. If it's a very large number, like we have products over reactants equals this K, then we know that if it's an extremely large number, there's a lot of product with very little reactant. The reaction tends to be way, 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 way toward the products. But if it's an extremely small number, that means we have very little product and mostly reactant. And as written, the balanced equation, reaction tends to be more toward reactants. That's a general conclusion we can draw from the value of K. Okay. Notice that they've put this subscript EQ down here, because in chemistry you have lots of Ks, lots of constants for almost everything. So this designates an equilibrium constant. But we can change this to be lots of different things. If it's an equilibrium for an acid dissociation in water, we might make Ka our value. Or if it's actually water has a special, right? Water can dissociate, pure water can dissociate into hydrogen ions and hydroxyl ions. We can do this. In solution. So you can take concentration of this one times the concentration of that one. And normally you would divide by this one, but there's a special rule for that. If we have pure liquids and pure solids in the equation anywhere, then they are not included in the equilibrium expression. So this is a liquid. These are in aqueous solution, so they're included. So the Kw would be concentration of hydrogen ions plus times the concentration of hydroxyl ions divided by nothing, because we leave out pure liquids and solids. Why? Because their concentration doesn't change. Only aqueous solutions and gases change concentration during the reaction. This one is extremely important for understanding how acids and bases work. Let's see, is that next chapter? Yeah. So I'll go ahead and do this one here. The value for this is extremely small. It's equal to 1 times 10 to the minus 14. So water is mostly that in its pure form. Right? You don't add anything to it. And just a little bit of it is this and a little bit that. Okay. So that tells us that that's actually our neutral state. Okay. What happens to the equilibrium constant when we change the temperature? Well, the equilibrium constant does change when we change the temperature. For the reactions where the forward reaction is exothermic, the KEQ will decrease with increasing temperature. So let's see if we can make sense of that. Oh, okay, we've got an illustration here. The best way to think of exothermic and endothermic reactions is with reactants yield products, and then exothermic is going to have a heat term on the product side because it's making heat as a product. It's giving up heat. So it gets hot. Endothermics will have this term for heat on the reactant side. It goes into the reaction and disappears. We're adding heat from an external source, which gets colder. So delta H is our expression for heat. It's actually a change in this fancy word, enthalpy. Which I don't think you need to know. I just thought I'd throw it out there because you may be wondering what delta H means. Just saying, well, H is heat. So with writing it this way, then for reactions where the forward reaction is exothermic, increasing the temperature will decrease KEQ. Increasing the temperature. So what we're doing when we increase the temperature is we're adding this term into the reaction. And what happens when you increase a product term? You shift it toward reactants. So if we add this term by increasing the temperature, we're decreasing the products, the numerator side, and increasing the reactants, the denominator side. So that decreases the K. It makes the K less. If we increase the temperature for an endothermic reaction, we're driving the reaction toward products, which increases the products and decreases the reactants and increases the K value. That's the logic behind the temperature dependence of the K value. Okay, I mentioned this one already. If the K is large, we're producing mostly products. If it's very small, we're producing mostly reactants. Now, there's a difference between the equilibrium constant and the equilibrium position. The constant is just that. As long as the temperature doesn't change, it is constant, no matter what the concentrations are. If it's at equilibrium, the concentrations could be anything. And in that ratio, they will give you that value. But in the process, say we disturb the reaction and it shifts the concentrations. That's a change in equilibrium position, but it doesn't change the constant. So there's a distinction between those two, between a constant and a position. We can have any number of different concentrations of reactants and products producing that value, but each one is a different position. All right, let's see. You have to take this graph, this table with a grain of salt. It's true. When the K is very large, you're essentially products. As it gets smaller, you get maybe more products than reactants, but not so much more. When you're close to unity, or between 10 to the third and 10 to the minus third, in this case, they're saying, you basically have significant amounts of both reactants and products. And that's true. But if they ever say that K equals 1, and that means concentration of products equals concentration of reactants, can't be. I mean, it can't be a blanket statement. Why? Because the K incorporates powers. Actually, let me do that this way. We normally put C and D on the other side, so we'll do like this. And then A on this side as a reactant. And B is maybe another reactant. So it's impossible to tell if this is going to be equal to 1 if these values are equal to each other. Because depending on the balanced equation, you could have almost any combination of powers in there that would just mess that up. And so we can say that if it's in this range around unity, okay, I'll go with that. You can have roughly similar amounts of each. And for that reason, because of these powers, the Ks are never quoted with units of measure. Because the sky's the limit. You'd have some really weird combinations. So we just have to take extra caution when we write the expression and use it in calculations in order to get the answer, right? If we're looking for, we know this value and we know this one, this one, this one, and we want to find that one, then we have to be careful that we're using the proper units here that match this. Well, actually, it's either, we have to know whether this is in terms of molarity or partial pressures. That's the first key. And then if we take great care, then we usually come out with the right answer. But units of measure are never quoted with a K. And it should say though, if you look at a reference manual for standard K values at a given temperature, then it should say whether this is reference to molarity or to partial pressures. Because they will be different values. Okay, no solids or pure liquids. What's the equilibrium constant expression for this reaction? Assume no solids or pure liquids. Okay, in that case, all the terms are part of it. So this would be in the numerator squared. These two would be in the denominator to the first power. So let's see, HI squared. Here we go. I think D is probably the right one. Okay, we're getting close to the end, aren't we? Le Chatelier's principle. Yeah, just a few more slides. I mentioned Le Chatelier before. It obviously is a Frenchman. But if it wasn't clear the way I expressed it before, if we have an equilibrium system and we apply a stress to it, and we use this general term because stress can come in many different forms. If we apply a stress to the system, then the system will react in such a way as to reduce the impact of the stress. And the one we looked at before was changing concentrations of reactants or products. But there are other types of stresses that can be applied. When you say a reaction shifts to the right or to the left, that only has meaning if you are referencing a balanced equation. So for our labs next week, if you answer questions and say the reaction shifts to the right or to the left, you better also include a balanced equation. Because if you write the equation in reverse, if you flip it, then the answer is wrong. I mean, you're not saying what you mean to say. If you say it moves to the right, but you meant it to be flipped the other way, then your description is not in accordance with the balanced equation. So you need to have a balanced equation in order for right and left to mean anything. Okay, we talked about concentration changes already. If you decrease reactant or product, the reaction will shift in order to replace that removed product or reactant. Or if you add more, it'll shift to consume part of that until equilibrium is reestablished. That's an easy one to understand. Let's see. Okay, that's nothing new. This is your author's idea of an explanation. And okay, we'll look at this. This is the equilibrium situation for nitrogen and hydrogen reacting to produce ammonia. And in this case, we're going to increase the hydrogen. That upsets the equilibrium. So we add more hydrogen. So what happens? Well, part of the hydrogen is consumed. But notice 3 plus 7 is 10. And we don't go back down to 7. We only go back down to 8.3 in this case. But we do use up some nitrogen according to the reaction, and we produce more ammonia. Okay. Now, if you know the equilibrium constant, say if we use these values here to calculate the equilibrium constant. So 5 squared, right, for ammonia, and hydrogen 7 cubed, and then nitrogen is a single coefficient, so it would be 5, right? If we use that to calculate a value, then 5 into that one means that one's gone and that one's 5, and 3 cubed is, let's see, 49 times 7. 4, 5 and 28 is 63. 634. So 634 divided into 5. And I need a calculator for that one. I can do it long division, but the risk of making a mistake is just too great. So this would be 7.88 times 10 to the minus 3. Okay, so there's our equilibrium constant based on those data. Now, when it shifts, right, we add this, and when it shifts, this expression should be equal to that one, right? We should have 6.1 squared divided by, let's see, hydrogen, yeah, let's do hydrogen, 8.3 cubed times 4.4 for the nitrogen. Now let's see if that works. 6.1 squared, and then 8.3 cubed. And divide that into it, and then divide this one into that. 1.48 times 10 to the minus 2. So they're wrong. I don't know where they got those numbers, but they're not right. Not if this first one. Let's see, did I put them in right? 8.3 cubed. Yeah. 4.4. Yeah. Ammonia. 6.1 squared. Yeah. That should work. Did I do this one right? Oops. My mistake. Maybe they are right. $1.46 times 10 squared. Okay. I apologize. They were right. Within experimental error. Okay. So the shift reestablished equilibrium. All right, what do we do with temperature change? We started talking about that before, where we were saying what happens to the K value when you change the temperature. But if you look at it in terms of Le Chatelier, it works just as well. If you have a reaction at equilibrium and you change the temperature, it depends on whether it's endothermic or exothermic as to which way it will shift. And placing the heat term as a reactant for endothermic or as a product for exothermic allows you to do that. Because if you increase the temperature in exothermic, you shift back toward the reactants. Whereas an endothermic reaction will shift toward products. Here's an example, right? They're going to put this solution, cobalt chloride ion in solution. If you cool it down, let's see, temperature change. If you cool it down, it becomes more pink because the cobalt combines with water to form this complex ion, which is a different color. So we've changed the temperature and shifted it toward the right based on this equation. All right, what happens to pressure? If you change the pressure, how would you change the pressure of a reaction? Well, if you're dealing with a pure liquid or a solid, doesn't matter. They don't respond to pressure. Besides, they're not in the expression anyway. So we're really talking about gases. Only gases respond to a change in pressure. But it depends on how the pressure is applied. If you change the volume, you've got a reaction of gases in a closed container, and it's at equilibrium. Then if you have a piston in it and you squeeze it down, you're decreasing the volume, but according to Boyle, you're also increasing the pressure. So by changing the pressure that way, what the system tries to do is reduce the number of gas molecules. So in this example, we've got a reaction at equilibrium where you have a mole of nitrogen and 3 moles of hydrogen reacting to produce 2 moles of ammonia. Yeah. This is exothermic, right? Which doesn't matter in this case because we're only changing the pressure. So if you increase the pressure by decreasing the volume, which way is it going to shift? It's going to try to make fewer gas molecules as a response to that increased pressure. And since you have 4 moles on this side, 3 plus 1, it's going to shift to the right to make 2 moles. Okay. If we increase the volume with our piston, decrease the pressure, then it's going to try to make more moles. And you'll make more reactant instead. Okay. What if we increase the pressure by injecting, say, an extra 10 moles of argon into that vessel? Increase the pressure. What's going to happen? Nothing. Because argon's not part of the reaction. And we didn't change the volume. Right? So we didn't change. The key here is, let's see, Dalton's law of partial pressures. Remember that one? The key here is that we didn't change the partial pressure of any of these reactants or products by injecting argon. Right? So they don't feel any change at all in their equilibrium position. Because all we did was just add an inert neighbor to the mix. Now, if you inject nitrogen gas in there, yeah, it's going to shift to the right, just like before, changing concentration. Okay, now what happens to equilibrium when we add a catalyst? One word, nothing. Catalyst does not change equilibrium. Catalyst only changes the rate of reaction. And in fact, it changes the rate in both directions. So that has no effect on the equilibrium. Now, it'll get to equilibrium faster if it's not already there. But if it's already at equilibrium, adding a catalyst does nothing. It just speeds things up. All right. So what factors affect the equilibrium of reaction? According to Le Chatelier, these three that we've studied: concentration, temperature, and pressure. Not catalyst. It has no effect. Okay. Let's see. Do we want to spend time on this? A breathalyzer. Everybody wants to know how a breathalyzer works. It's used to detect alcohol levels in a potentially intoxicated driver. The chemical reaction changes color from reddish orange to green in the presence of ethanol in the breath. So if there's ethanol in your breath, it will react with potassium dichromate and the little sulfuric acid they have and produce these compounds, which makes a reddish orange color. I think that's probably due to this one right here. Okay, in this reaction, let's see, in this reaction, which one is undergoing reduction? Ooh. Which one is being reduced? Well, let's see, potassium didn't change. Chromium, we've found this one to be +6 before. So what is it over here? Well, this is 3 times 2 minus, right? So it's -6 total. Sulfate didn't change. Sulfate's the same, so we don't have to worry about sulfur. So that's -6. That means this chromium has to be +6, and each one is +3. So +6 to +3 means chromium is reduced, undergoing reduction. So this one, chromium 6+ undergoes reduction to chromium 3+. So these two are accurate. While which one is undergoing oxidation? Well, it's not the sulfur, but this ethanol is being oxidized to acetic acid, right? This is one way of writing acetic acid. The other way is the way that we normally see it, like this. Same thing. So what's happening here? This one is being oxidized to that one. So this one, let's see, that's the same in both of them. It's being oxidized to this one. And, the oxidizing agent is the one that's being reduced. So this is the oxidizing agent, this is the reducing agent. Okay, so C would be the answer for that. Come on. There we go. Fill in the blanks. There. So that's what happens when you get stopped and have to breathe in a tube.